Hello, everyone.
Hello.
Anybody have any questions before we get started?
I just have a general question.
Go for it.
I've sent you a couple of emails and I just wanted to know if you were getting them.
I did see your name. Let me see if I ever read them. That's a whole different story. Sorry about that, but that's the state of my life right now.
I understand.
I'm in the wrong folder. No wonder that didn't help.
That's okay. None of them are really important right now, but if I could talk to you at a later point, would that be okay? Or
Yeah,
maybe...
absolutely. If you want to stay after today, I can do a breakout room if more than one person's there, and we can talk in private that way. Or if you can talk in public, that's okay too. But either way, I'll turn the recording off. Yeah, I see your emails.
Okay.
Yeah, I knew I'd seen them. I just couldn't remember. Nope, I didn't answer them. You sent the last one. Last one I found was Tuesday. I'm sorry. Good Lord, I missed that far. Ooh. Anybody else have any other questions? The deadlines on the homework should be proper now. They're, of course, that's only chapters 1 through 10 plus 36. Any other chapters are obviously have dates that are irrelevant. Chapter 43 will be extra credit, but it's not yet. Okay, that will have, and those ones that are beyond what we're covering, they should be towards the end of the semester. We're going to jump from chapter after 36, we're going to 11, and then from 11, I think we're going to 14. So usually I'll make a couple extra credit assignments for 12 and 13 that you can get extra credit for just to complete the chapters that you missed, but that's not really required. I usually do that when I usually make them required like a couple weeks after we start 13 or 14. So those will be some extra credits. If we finish 14 and 15 and we still have time, then we'll go into like chapter 43 or something. And that may or may not become extra credit. Usually does, but may or may not. Yeah, in fact, we're going to talk about a muon today as well. So all right, well, I guess we'll get started. Last time I introduced you to a little bit of the history and the introduction to the special theory of relativity. And in fact, using the two principles of relativity, the first being the laws of physics are the same for all inertial observers. And I taught you how that inertial observer thing was Einstein's way of cutting out gravity. And then the second law was the speed of light is a constant independent of the motion of the source or the observer. And that was a whole different weird kind of thing that I showed you once I applied it to a simple train car with a special kind of clock in it. We got something called time dilation. And that time dilation said that basically you have to multiply the proper time, which is a time measured by someone who's not moving relative to the clock they're using. And you have to multiply that by 1 over the square root of 1 minus v over c quantity squared. That 1 over the square root thing is called gamma. So you can say I have to multiply my proper time by gamma to get the time that someone on the side of the railroad track or the side of the road or the side of the spacecraft trajectory to see that's the time that they would measure. So we didn't actually do any examples with it. I just hinted to you that gamma is always 1 or larger, so that the regular time is always greater than the proper time. And I wanted to stress to you that proper doesn't mean the correct one. It just means one in which the time clock that you're reading is not moving with respect to you. So the regular delta t, the one without the subscript 0, refers to time that you would see passing on a moving clock. And of course, if you happen to be in the train, you need to argue that you're not moving because you're looking at your clock. But if you look at someone else's clock off the side of the train, now that's moving with respect to you. Now you've become delta t. You've become the one that measures delta t. And they, on the other hand, even though by your understanding of the world, how the earth is sitting still in some sense and the train is moving, still that person's the proper time now. Okay. And both of you are right. There's no right or wrong about it. So that's what I was trying to stress by the word proper. It's of German origin, and it's not really not to be taken as correct versus incorrect. Both of those are correct times. All right. So I also asked you and suggested to you guys to take some time to work out some gammas, specifically gammas that came up to whole numbers. So I'm going to show you how to do that, but I'm also going to go ahead and show you some examples of it. And then I'm going to go to applying the time dilation formula. I'm going to introduce another formula and so on and so forth. So let's turn my document cam on. So what we learned last time was a couple things. We learned about the two principles. The speed of light is a constant independent of the motion of the source and the observer. That's one of them. And the first one was the laws of physics are the same for all inertial observers. And from that, we were able to derive this expression that said the time interval measured by someone that considers themselves not moving, delta t, is equal to gamma times the proper time, which means the time interval that the person measures on the train, say, by their own clock that's on the train with them moving at the same speed as them. Okay. And in this case, gamma was defined such that this whole quantity is this. And of course, that means gamma is technically defined to be 1 over the square root 1 minus v over c, quantity squared. And that is greater than or equal to 1. And it can also be written as gamma is equal to 1 over the square root 1 minus beta squared, where beta is defined to be v over c. So if they say has a relative speed of 0.3, that means 30% of the speed of light, and they're saying beta is equal to 0.3. Okay. So what we know is gamma is equal to 1 over the square root of 1 minus beta squared. What I suggested is you guys find all the betas that give you gamma equal to 1, 2, 3. Obviously, 1 is known. That's going to be 0. 3, 4, 5, 6, 7, 8, 9, and 10. And then we start jumping to say maybe 100, maybe 1,000, maybe 10,000, and then maybe 1,000,000. Okay, so just want to show you algebraically how to do that. You can square both sides. You get gamma squared is equal to 1 over 1 minus beta squared. Then, of course, you can change that a little bit and say 1 minus beta squared is equal to 1 over gamma squared. And then you can change that a little bit and say that beta squared is equal to 1 minus 1 over gamma squared, which if you get a common denominator becomes gamma squared minus 1 square root. Well, actually, once I take the square root of that, it'll be square root over gamma. So beta is actually equal to the square root of gamma squared minus 1 over gamma. Now, really, this is nothing about physics right here, okay? This is just seeing the useful things you can do to make physics a little easier, or to make relativity a little bit easier to talk about. So now that I have that expression, let me share my screen with this little doohickey. So what I've done here is I actually took a Microsoft Excel blank sheet, and created a formula. So here's my gamma values of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 10, 100, 1,000, and 1,000,000. And then I happened to use 38.8 for a particular reason. But all I really did was basically put in that formula I just arrived at, which is the square root of gamma, which is this value right here, A2. Okay, so that's squared minus 1, take the square root of all that, and then divide it by gamma. And these are the values you get. So you can see this one actually turns out to be 0.866025, which you might recognize before as root 3 over 2. So if you want to find the integer values, all you do is look for things that are going to make this this quantity one of these integers. So these values are wonderful. They give you, percentages that are easy to calculate. These are all beta, by the way. And then, of course, the speed of light, or their actual speed, or the velocity, would be this number times the speed of light. And the speed of light, of course, is c, which I'm writing it down here. I'll put on the document cam in a second. But it's c, and it's defined to be exactly 299,792,458 meters per second. And it's exactly that to any number of decimal places, specifically because we define the meter to be the distance light traveled by 1 over 299,792,458 of a second. Okay, eighths of a second. So now it's exactly that. So now that you see this, you can see obviously for gamma equals 2, we get beta is equal to the square root of 3 divided by 2, which is approximately 0.866025. But you can do other ones just by setting these to whole numbers. So now that you've seen this and you know how I programmed it, for instance, again, square root of beta squared minus 1, all that divided by just beta, or excuse me, just gamma. I keep saying beta. So there's the stop sharing. So now you can see this is the speed of light that I just told you I would show you, 299,792, or 299,792,458, which is approximately equal to 3.00 or 00 times 10 to the 8th meters per second. Okay. So if I tried to find basically things that will come out of this as be whole numbers, I'd want to use gamma squared minus 1 equaling a perfect square. So another way of looking at that is say that, well, just if you wanted the square root, we've already had or seen the instance where the square root came out to be 3, because that was right here, root 3 over 2. But what if you wanted the, or excuse me, can't turn out to be 9 or something like that. If you wanted this whole factor under here to be 4, then you'd say gamma squared minus 1 equals 4. That's gamma plus 1, or 4 plus 1 is equal to gamma squared, and that's 5. So that's the square root of 5. So you could put square root of 5 over 5, but that's not going to give you a nice unit. Or you can try another one like, let's say this whole thing becomes 9. And then, of course, gamma squared minus 1 would be, again, square root of 9, which would just be 3, and then over 2. So you can find all those different copies like that. But the more important thing is that just gives you an easy way to think about what this gamma factor is, because this gamma factor is going to appear over and over again. What it is, remember, is a number that's 1 or larger. So when it's right here, it's actually multiplying by the time the person measures on a moving aircraft or something. It's multiplying by it, so it's how much bigger the time is. And just like your eyes dilate, right? When your eyes dilate, the hole in the middle gets larger and larger. So what they're saying here is this is time dilation, because the time that the person on the train sees is getting bigger to make the time that you see. So your time is getting has been dilated in some sense. Now, with that in mind, since this gamma is going to appear all over the place, it's good to know when that gamma is 2, or when that gamma is 3, or when that gamma is 4 or 5 or 6 or 1,000 or something like that, because it turns out length has 1 over gamma in it. Turns out kinetic energy is gamma minus 1 parentheses mc squared instead of 1/2 mv squared. It turns out that momentum isn't mv anymore. Momentum is going to be gamma mv. So this gamma appears over and over again. So I definitely recommend you make a spreadsheet, maybe even a graph of gamma versus beta, just so you can see how it's going to, asymptotically approach infinity. So with that in mind, I'm going to start to tell you some things about the world and about the evidence we have for special relativity. Basically, special relativity is the single most tested and most successful history in the history of mankind, theory in the history of mankind, and it's theory in that proper strong form, not just a theory. It's actually a theory, which we say is a very strong word. And the reason why is because we use this in particle accelerators all the time. Specifically, we use particle accelerators to bash things together. And in that case, you might get tens of thousands of collisions every second. And no human can possibly do that. So we have to write computer codes that look for anomalies in those types of collisions. And one of the anomalies happens to be a violation of special relativity. So we might run those accelerators for months on end and get literally thousands or tens of thousands of collisions every second, and never once have we found a single violation of the special theory of relativity. And that's just considering one accelerator, but in fact, there's tens of thousands, if not millions of accelerators all over the planet. So it's really the most tested theory in the history of mankind, and it's never been found wanting. So one of the first things that makes it obvious that we need it is the observation of muons. There's these particles called muons that are created in the upper atmosphere, let's say about 1.5 kilometers above the Earth's surface. And they're created basically when sunlight, basically electromagnetic radiation from the sun, as well as particle radiation from the sun called the solar wind, when they interact with the upper atmosphere, they can actually cause more or less nuclear reactions that create muons. And a muon is sort of like a really heavy electron. That's sort of what it behaves like. In fact, it's on the order of 1,000 times heavier than the electron. And these things, like I said, are created about 1.5 kilometers above the Earth's surface. And we find them down here at the surface of the Earth going somewhere between 70–80% of the speed of light and 90–96% of the speed of light. Well, that's kind of a weird thing that we find them at the surface of the Earth. Literally at sea level, we are able to find them, because if you multiply their lifetime, which is about 2.2 microseconds, if you multiply that lifetime times that speed, you'd find that that's not enough time. In other words, that distance that you get when you multiply velocity times time, that distance is less than 1,500 meters. So how do we actually explain the fact that muons make it to us? So that's the problem we're getting ready to solve right now. So let me turn on my document cam again and say, example 1. Ignoring relativity, somebody just came in. Ignoring relativity, how far can a muon travel during its 2.2 times 10 to the negative 6 second lifetime? If it is moving at 86.6% of C. So there's our first question. Ignoring relativity, how far can a muon travel? So I could actually write that word, or I could just use the symbol like I did. How far can a muon travel during its 2.2 times 10 to the 6th second lifetime if it is moving at 86.6% of the speed of light? Well, anybody know what formula, what kinematic equation we should use for this? About that. The average velocity is the distance traveled divided by time taken. This is not a 2 up here. This is just a thing where my paper moved. Okay. Because what we're going to have is not an average velocity. We're going to have an exact velocity. So the average velocity and the velocity being a constant means the same thing. Our initial position is going to be at 0. So we'll say that X is actually equal to V times T. And in this case, we're saying 0.866, which I think you guys will recognize is √3/2, but that's the beta. When they tell you 86.6% of the speed of light, you convert that to a decimal. That is the beta value that I've been talking about. So I'll multiply that by 3.00 times 10 to the 8th meters per second, and then multiply that by 2.2 times 10 to the negative 6 seconds. When I do that, I see that 3 e to the 8 times 0.866 times 2.2 e to the negative 6 gives me a whopping 571.6 meters. And in fact, these last two sigs are not even sigs. Okay, so you see that's clearly not enough, not far enough to hit sea level from 1,500 meters up. So that's a big deal, right? We know for a fact these muons actually make it to the surface of the Earth. We've detected them here. And like I told you, they can come at varying speeds. And we find that the mean lifetime of them is 2.2 times 10 to the negative 6. In fact, they have different lifetimes. And they have other things that are going on too, because they tend to interact with matter on the way through the atmosphere. So you got to take into account all that stuff. But generally speaking, they should not be making it to the surface of the Earth. But if we think about it from the standpoint of relativity, that's going to give us example 2. And what we're going to say is, if a particle is moving at beta equals 0.866 and its lifetime is 2.2 times 10 to the negative 6 seconds, then how long will we see it live? So if it's traveling at beta equals 0.866 and its lifetime is supposed to be 2.2 times 10 to the negative 6 seconds, how long will it live? Anybody have an idea what we're going to use for this? I have not yet seen the Boba Fett trailer, by the way, but I will check it out tonight. All right, well, I didn't get any takers on this answer. So remember, when the particle is moving, it's sort of materialistic or I don't know, biological clock is ticking along with the muon. In other words, it's moving at the same speed as the muon. Therefore, the muon doesn't see the time that we see. The muon sees proper time. So that means delta T0 is equal to 2.2 times 10 to the negative 6 seconds. And what we're asked to calculate is how long that appears to us. So we're asking delta T equals question mark. Now, because I know this number, I can immediately figure out that it's going to be a factor of 2, but I don't want to go through that process. I want to actually go through the multiplication process. So I'm going to say delta T, according to our time dilation formula, is equal to gamma times delta T0. That's where I just say, well, 0.866 is basically gives me root 3 over 2. And I know when I put root 3 over 2 in for beta, I end up getting 2 for my factor. So it should be 2 times that, or 4.4 microseconds. But let's look at that and see how it happens. So I'm going to say 2.2 times 10 to the negative 6 seconds over square root 1 minus 0.866 squared. Now you can see if that was beta equals root 3 over 2, then when I squared that, that would become 3 over 4. And 1 minus 3 over 4 is 1/4. And the square root of 1/4 is 1/2. And 1/2 in the denominator is the same thing as 2 in the denominator in the numerator. So I'd get 4.4. But of course, we're actually using a rounded version of that. So I'm going to go ahead and calculate what it is. And what I get is 2.2 e to the negative 6 divided by parentheses square root 1 minus 0.866 squared. And I get 4.39 times 10 to the negative 6. Which of course you can see rounds to 4.4 just exactly as we expected. So the half time is actually twice as long. If that's the case, then how long should it be able to travel? So example 3. Given the answer to example 2, how far should the muon be able to travel? So anyone know what kinematic equation we want to use now? I want to see how far, like in meters or whatever, it can travel. Yes, Jared says VT. Yes, distance is equal to velocity times time. So we can just say distance is equal to velocity times time, like we said in example 1. In this case, we're going to get 0.866 times 3.00 times 10 to the 8th meters per second times. Now we're going to realize in our frame, the time period is going to be 4.4 microseconds. So I'll say 4.4 times 10 to the negative 6 seconds. And lo and behold, this should give us a quite a bit larger value. So so what I'll get is 0.866 times 3 exponent 8 times 4.4 exponent negative 6. And lo and behold, I'll now get 1,143 meters. Okay, still not quite the 1,500 meters, but like I said, the ranges of velocities range from V ranges from 0.6 to 0.96. I just did a 0.866 just to make for easy math and to show you how easy you get a gamma equal to 2 by using that. So yeah, clearly if I took one of these higher velocities, maybe it'd be 96% of the speed of light or 94% of the speed of light or something like that, which muons also are found to travel at, then we can find this to reach the 1,500 meters easily. So that really is our explanation for why muons are actually detected at the surface of the Earth. Is because their time is actually dilated by traveling so fast. Remember, the rule for time dilation is that moving clocks run more slowly. So it takes a longer period of time to tick out 2.2 microseconds. So because of that, we can say clearly the muon is going to live long enough. But here's the problem. That explains to us how the muon makes it. But if the muon were perhaps to have a who, you know, Horton here's a who from Dr. Seuss. If the muon happened to have, say, a little who living on its back, that critter would have to agree at the end of the day that the particle hit the surface of the Earth as well. But according to it, the muon was not moving at all, right? So it can't see time dilation as saving the day. Anybody want to guess what might actually save the day and make sense from it, for it from the WHO's perspective? Anybody have any idea? Think about it a little bit. From the WHO's perspective, how does it make any sense that the muon makes it to the surface of the Earth? There's no time dilation that can happen. Okay, well, let me give you an answer by asking another question. I'll call this an example. And we are on example 4, if I'm not mistaken. So yeah, I'll call this an example. Example 4. A spacecraft is moving at beta equals 0.866025 for a time of 1 year. Actually, of a time of, let's say, a time it considers, or it measures, let's say it that way, a time it measures to be 2.3 years. How far does the spacecraft think it traveled? And obviously, I mean the people on the spacecraft. So according to the spacecraft, it knew its velocity is 0.866025 times the speed of light. So we'll use distance is equal to velocity times time. Now, the time it measured is actually time t0. So it's going to be 0.866025 times 3.00 times 10 to the 8th, that's a decimal there, meters per second, times 2.3 years. Now, what I would want to do is convert that all to seconds, but check this out. I can also change the units here from, meters per second, 300 million meters per second, to 1 light year per year. Does everybody understand that that would be the speed of light as well? That's the very definition of the speed of light, and the very definition of a light year. A light year is the distance light travels by during 1 whole year of traveling. So if I do that, then I can see 0.866 times 1 year times 2.3. Actually, that's supposed to be 2.6, wasn't it? Oh no, that's 2.3. Yeah, that's cool. Okay, so what happens here is now that years is going to cancel out with this year, and I'll get a certain number of light years. So I'm going to say 0.866025, and let's say that 2.3, we can imagine that to like 4 or 5 decimal places. That's no problem. So 0.866025 times 1 times 2.30000, and in that case, I get roughly a distance of 1.991858 light years. So that's how far it traveled. But here's example 5, and this is going to give us something really big here. So let me go back to a black pen for a second. Example 5. We watched the spacecraft travel for how many years? It's a weird way of wording it, but I worded it as a question. I changed what I was going to do at the last second. So we watched the spacecraft above travel. How many years did we think it traveled? Anybody know what we're thinking about? Yeah, no problem, Victoria. Can anybody put a name on the type of time? Either this is the 2.3 years, or this is the number of years we're getting ready to calculate. Can anybody name which one of those times is, say, the proper time? Okay, a lot of people would think that that's normally the scenarios. Most people think we would be measuring the proper time, but the spacecraft is the one who measured its time on the spacecraft. So the clock, or its biological clock could be used, in fact, is not moving with respect to the people on the spacecraft. So that's the delta T zero. That's why I put the 0 there, or the O there, whatever way you want to call it. So what we're looking for in this case is the actual delta T. But delta T, of course, is gamma times delta T 0. So that means I'm going to take 2.3 years and multiply it by 1 over the square root of 1 minus 0.866025 squared. And when I do that, I'm going to get 2.3 divided by square root 1 minus 0.866025 squared. In this case, I get 4.599994 years. So we actually observed the thing moving for quite a bit longer. And we would say, no, it didn't take you, 2.3 years. It took you essentially 4.6 years. Now let's look at example 6, and then I can go ahead and do a derivation that will make all this make some sense. So example 6 is going to be since me, evidently I'm going to write, since we saw the spacecraft travel at beta equals 0.866025 for 4.600000 years, how far did it actually travel? And I'm going to say actually in quotation marks, because I mean with compared to us. So before we used the same type of argument to see how far the muon went, what equation did we use there? Because we need to use it now. Can anybody tell me what equation we're going to use now? We know it's speed. We know it's years, or it's time. Anyone? Yes, define distance. Yes, distance equals velocity times time again. So distance is equal to velocity times time, which remember is the same thing as that v bar equals x minus x0 over t. Okay, so in this case, we're going to go 0.866025 times 1 light year per year. Remember, we're using years. This works out a little better for us. Times 4.60000 years. And basically, I'm just rounding that. Okay. And because of that, I now see that the distance it traveled was 0.866025 times 4.6. So that'll give me 3.9837 light years. Okay, so what seems to have happened here is we know the distance between Earth and some distant place that the spacecraft flew was about 4 light years away, right? And according to the spacecraft, that distance was closer to like 2 light years away. Well, that means what we found was a length. We found a length equal to v times delta t0. But then since delta t is equal to gamma delta t0, we know that delta t0 has to be equal to delta t over gamma. Well, v delta t is actually the length measured by us who saw us and the place that the spacecraft went as the same, moving at the same speed. In other words, sitting perfectly still. So this turns out to be L0 over gamma. That's the actual proper distance. The proper distance is the distance measured by the person who didn't move through the proper distance. In other words, they just happened to sit there at one end and knew the other end was a certain distance away. Whereas the person that actually saw that distance from Earth to, say, Alpha Centauri, that person is actually traveling at some speed relative to it. So this is the proper time. Excuse me, I said proper time. This is the proper length. And we have a new formula. The new formula is that length is equal to proper length divided by gamma. So as I warned you guys, the gamma is an important factor that's going to come in over and over and over again. So what this says is that moving lengths are contracted. Again, this is like your eyes being constricted. That's sort of the same word here, using contracted. That means it's going to shrink. So a Crown Vic, which is what we used to use for police cars, they're really long and Cadillac-like, for instance. If we see one moving at some speed v that's appreciable factor of speed of light, then we're actually going to notice a difference. And it actually only affects the dimensions parallel to its motion. So the height will stay exactly the same, but the wheels will become sort of elliptical like this. And that means the windshield is going to be steeper like that. So this is what happens. Cars, when they move large speeds, shrink along the direction of motion. In other words, you can make a Crown Vic turn into a Volkswagen Beetle, at least in terms of length. Moving lengths contract. And remember, proper length is the length measured by someone not moving relative to it. So proper length is the length measured by someone that does not see that length moving. And proper time is time measured by a clock and someone moving, reading it while it too is not moving. So if the thing you make the measurement of or use for measurement is not moving with respect to you, then you're measuring it properly. Okay. If you happen to be moving through that length while measuring it, then you're measuring the improper length and it's going to be contracted. If you're watching a clock go by, then you're going to experience a non-proper time while the person riding along with that clock is measuring proper time. So that's the key to understanding the subscripts. Anybody have any questions on that? All right, now that we've learned that, can anybody now figure out how the WHO can explain that the muon, which only has a half-life according to the mu, according to the WHO, only has a half-life of 2.2 microseconds. How does the WHO reach the conclusion that the muon makes it to the surface of the Earth, which it clearly does, because the muon, the WHO was riding the muon when it hit? Yes, someone answered it on the chat. And I think that's Jared. Yes, that was Jared. And that's exactly right. According to the WHO, just like the spacecraft flying, say, from Earth to Alpha Centauri, that spacecraft saw that distance is only about 2 light years because it was moving relative to the distance. So just like the WHO, when it's riding on the back of the muon, it doesn't see that muon, or it doesn't see the Earth's atmosphere as being 1.500 meters. In fact, if the muon is traveling at 0.866025 meters times the speed of light, then we know its gamma factor is 2, so it would be 750 meters thick. So yes, and that's why we have to have those two. One has to go up and the other one has to go down, because look, velocity in general is distance divided by time. If we're going to set a particular velocity, the speed of light, for instance, equal to a constant that can never change, then one or both of these things is going to have to change to accommodate that weirdness. In the first case, we saw that the time changed. In this case, we see that the distance changed. And in both cases, we needed it to appear as if the velocity was larger. So, or excuse me, as if the velocity were sort of, or the distance traveled, let's write it this way, as if the distance traveled was not quite as far. So the distance traveled being not quite as far, that means I have to have a low distance, or I could do the same thing with having an extended time. So the extended time was actually time dilation, and the decreased distance was in fact the length contraction. So distance had to go down, or time had to go up. And that's why we have those two things. It was perfectly natural for them to come out. There's no way it couldn't have, if we're going to try to fix a particular speed so that it's always a constant. So that brings me to, well, let's see. So let's look at the who. So example 7, maybe. Yes, example 7. According to the who, how fast is the Earth's surface moving toward it? Anybody tell me that as a beta? And then part B, how thick does the who believe the atmosphere is? So anybody can answer part A? If you need, here's the old question. Since we saw the spacecraft traveling at beta equals 0.866025 for 4.6 light years, this is the same thing actually, but not for the spacecraft, but for the Muon, we did 0.866 as well. So 0.866 was all it was doing when we did the Muon. So anybody want to guess what the speed is according to the who? So there's nothing magical about speeds. We haven't learned any things about speeds changing or anything like that. So really, if we see a Muon moving, thanks, Jared. If we see a Muon moving towards us at 0.866C, then the Muon sees us moving towards it at 0.866C in the opposite direction. You remember Vij equals negative Vji. So that's what we're talking about here. So yes, it's 0.866C. So part B, that means the atmosphere is given by L is equal to L0 over gamma, which L0 is 1,500 meters. And of course, gamma is approximately 2. So you see 750 meters, that being half of 1,500. Any questions on that? So now let's talk about something called the twin paradox. So the twin paradox is this scenario. And a lot of people get it wrong. I mean, I've actually seen publications by Time Life Books, for instance, get it wrong. So this is Earth sitting here. And let's say here's me and my twin brother. I don't technically have a twin brother. I have a brother that looks like me, but he's fat and ugly. And unlike me, he has no hair. I'm good looking and, of course, have full locks of hair and am not fat at all. That's my story. Okay. So what's going to happen is we're going to have a spacecraft fly by. It's some fancy looking spacecraft like this. Okay. It's going to fly by at 0.866025 C. Okay. So this is Billy. And this is my balding, uglier, fatter brother, Brian. I'm punishing him for not watching my YouTube channel. So, so I'm going to, having been the person that knows some physics, I'm going to teleport like they do on Star Trek. I'm going to teleport from Earth to the spacecraft as it flies by at 0.866025, the speed of light. And in fact, I'm going to travel all the way to the star system, Alpha Centauri. That's the nearest star other than our sun to us. And it's actually a binary system. It's about 4 light years. In fact, it's more like 4.6 light years away, but we're just going to call it 4 light years away. So I'm going to say this is approximately 4 light years away. And of course, when I get there, the spacecraft is going to be going like this, 0.866025 C. And there will be another spacecraft, just like the last one, traveling at 0.866025 C in the opposite direction. I'm going to teleport from it to this spacecraft, and then it's going to come by here a little later, traveling still at 0.866025 C, and I'm going to teleport back. So just to show what I'm doing, I am teleporting onto this one and then teleporting from this one to this one, and then teleporting off of this one back up to here. Okay, so that's really what's going on here. Now, the twin paradox is not this part that you're getting ready to see. So when I come back, basically this is going to take 4 light years divided by, or excuse me, 4 light years divided by 0.866 light years per year. So let's do that math real quick. I'm going to say 4 divided by 0.866025. I got to put parentheses around this because my calculator knows what it's doing and I don't. Times 1, duh. So actually it didn't matter either way. So in fact, this is going to take me 4.61 years, according to you guys. And then of course, when I get back, my brother Brian, when I get back, Brian is 9.24 years older. Than when I left. So he's now like 60 years. Let's say we left on our birthday. He's like 60 years and 3 months. Okay. So we were both 51 and 0 months when we left. Now, when I come back, I am, if I take that 4.62, when I multiply that by 2, of course, I got 9.24. Now, when I take that, I'm going to divide that by 2 because of the Lorentz, the time dilation. Because I was traveling at 86.6025% of the speed of light, my clock was running essentially 2 times slower. So I will actually have only aged by 4.62, and that should be a 2. I didn't round it properly. By 4.62 years. So I am 54 years and 7 months. Now, a lot of people, including that Time Life book that I read, think that's the paradox. That's not the paradox. That's just fact. Okay, there's nothing contradictory about that. They think it's contradictory because 2 twins have different age. No, that's just fact. It's 2 twins would definitely have a different age if they did this. Okay, what makes it a paradox is this. What if my brother says, oh, wait a second, this ain't cool. I'm not liking the scenario now that I'm the older person. We were the same age, everything was good. In fact, he's going to argue that him and the Earth just sat here for 9.24 years, and him and Earth and Alpha Centauri flew off this way, and then Alpha Centauri and him and the Earth then came back this way while I stood still in that spacecraft. And if that's the case, then Brian should be 54 years and 7 months old, and I should be 60 years and 3 months old. That's what the apparent paradox is, because really in physics we don't have real paradoxes. If we did, something screwed up, right? But you can actually tell which one actually did that. So if the universe was in fact a loop, a closed loop, and its radius, or let's say its circumference around that closed loop, was less than 4 light years, then yeah, there would be a paradox, because he could really make that claim. But because I literally had to take the spacecraft, go from 0 to 86.6% of the speed of light, and then go from 86.6% of the speed of light to 86.6% of the speed of light backwards, and then from 86.6% of the speed of light to the left back to the 0 at the spacecraft, I can actually do an experiment to determine which one actually did the moving. And in fact, the experiment could just involve fuzzy dice. If I had fuzzy dice hanging from my ears, say like earrings, then when I teleported myself from here to the first spacecraft, clearly the fuzzy dice would have shot that way. And then when I teleported myself from this spacecraft to this spacecraft, the fuzzy dice would have went off that way. And then when I teleported myself from this spacecraft to this to this planet, then the fuzzy dice would have went this way. Meanwhile, Brian's fuzzy dice hanging from his ear, which he normally wears anyways, they would not move at all. That's the actual solution to the paradox. You can actually do an experiment to tell which one moved. Therefore, Brian cannot claim that he is now only 54 and 7 months. He has to stick with the 60 years and 3 months, because I was the one that actually physically moved and experienced the time dilation that made my biological clock move slower at a rate of 1 to 2. So this trip that you guys on Earth said took me 9.24 years, to me, it only took 4 years and 4.62 years. So actually this should have been 55. I forgot we left at 51 years of age because that's how old I am. So it should be 55 years and 7 months. Y'all get that? That's the twin paradox. Any questions on that? Now there's another one, and I'll cover that, and then we'll probably call it a day. And that's called the ladder and the barn paradox. Now, the ladder and the barn paradox, again, is a paradox in quotation marks only, because someone had to have solved it, or Einstein would have been wrong. And, we know he's not wrong, because the theory of relativity is pretty freaking awesome, right? So let me tell you the story about the ladder and the barn paradox. So the story, the way I tell it is, and I tell them I'm going to NC State and stuff like that, because that's where my daughter's going. And I went there for a little while, and I enjoyed it there, even though I'm a ECU undergraduate and a UNC graduate student. But anyways, a boy goes off from his father's farm at college, and he's going to go to college and do things. He's ostensibly going to leave the farm and not work for the farm anymore, but he gets there and he discovers that he does like agriculture. So he comes back to the farm anyways. He comes back to the farm, but he's now got an education, a full education from a nice 4-year institute that in fact gives PhDs and all that good stuff, a very good university, NC State. And he's even had courses in physics and astronomy and astrophysics and cool stuff like that. And he pulls up into his dad's driveway, because he's going to stay there for a little while he gets his own farmland. And he looks over and he sees the barn and the stupid ladder, old wooden ladder, falling apart, sitting right next to it. He's like, Dad, I wanted to bite my lip, but I just couldn't do it. I've been here for 3 hours now. I finally got to say something. Why have you not put that ladder in the barn? And the father says, well, boy, I don't know what they've been teaching you up there at NC State, but it clearly is something that doesn't involve geometry or mathematics, but you can't fit a 20-foot ladder in a 10-foot barn. And the boy says, whatever. Okay, I've had courses in physics and calculus and mathematics, and clearly I know, because I did so well in these courses, I know that you can fit a 20-foot ladder in a 10-foot barn, easy peasy. And the father says, you think so, huh? All right, well, how you propose to do that? And let's go do a little experiment while we still got some daylight hours left. And of course, the boy says, oh yeah, sure, fine, no problem, no problem. He said, well, remember, son, I'm old, so I can't be doing a lot of hard lifting and squishing and compressing and running and stuff like that. He said, Dad, don't worry about it, I'll take care of it. Okay, well, what happened was the father, he went to NC State too, and he went through the same physics course, but he maybe learned a little bit more than his son did. Because when they got out there, and here I go back to drawing, when they got out there, the boy had a really perfect plan. He knew that if he traveled at 86.6% of the speed of light, the gamma factor would be a factor of 2. So the boy decides, here's my barn. And the barn, of course, is 10 feet from front to back. We're looking at it from the side. So the door will be up here. And here's the ladder. And this distance, of course, is 20 feet. And the boy is standing here like this, just looking at it, right? He says, all right, well, I'm going to travel at 86.6% of the speed of light. And what I'm going to get you to do is, when I get into the barn, when my front edge of my ladder touches the back edge of the barn, and the back edge of my ladder touches the front edge of the barn, I want you to shut the door. And then it'll be in there, albeit for a split second, but it'll be in the barn. And the father's just laughing, saying, okay, no problem, I'll do that. Well, then the boy starts to run. And the boy, when he's running, of course, he is in fact moving at 0.86 the speed of light. So the boy is now moving at V equals 0.866025 C. And the ladder is in fact still 20 feet long, according to the boy. And what's happened is, in fact, the barn is now 5 feet wide. Like that. And what he sees is the front edge of the ladder gets to the back edge of the barn while he's still standing out here with it running, and the other half of it's way out here still. And then he sees himself get into the barn, run through the wall like Wile E. Coyote, leaving an outline of himself in the ladder. And then the back edge gets here, And the boy is way the heck out here by that time. He's standing out here running still, of course. And his father's just now closing the shed. And the boy's been knocked a little senseless for running at 86% of the speed of light through a wooden wall. And the father's just rolling on the floor laughing, or rolling on the grass laughing. Okay. So the ladder in the barn paradox is, did the ladder fit or did the ladder not? Because from the father's standpoint, what the father saw was that the boy was in fact traveling at 86% the speed of light, and the ladder did in fact shrink to 10 feet. And in fact, the barn stayed the full 20 feet, or excuse me, full 10 feet. And in fact, when the boy was dead center, he closed it just like he's supposed to. So this is father's recollection. And this is the son's. Okay. So according to the father, it did fit. Well, he knew it all the time. He knew it was going to happen, but he also knew that his son was going to feel like an idiot because he got it so wrong. Unless his son was thinking a little bit ahead and knew this. But the paradox seems to be, did the father was the father right or was the son right? Did the ladder actually fit or did the ladder not fit? And that seems like a paradox, doesn't it? Anybody have any idea from your reading whether or not it actually is a paradox or how we might reconnoiter that or fix it? Well, if you read your book, there's a section called simultaneity. And one of the things that relativity screws with is the fact that there is no definitive synchronicity. Okay, one thing synchronous, two things that are synchronous in one frame is not necessarily synchronous in another. So this ladder did in fact fit in the father's frame, but it didn't fit in the son's frame, and that's okay in both cases. There's no did fit or didn't fit. There's just two different frames, and in one reference frame, the ladder fit, and the other reference frame, the ladder didn't fit, because what required to happen for fitting is the front edge of the ladder has to get at the back edge of the barn at the same instant as the back edge of the ladder got to the front edge of the farm, and the father closed the door. That happened in the father's frame. Those two events were synchronous. However, in the son's frame, the front edge got to the back edge, and then a split second later, the boy got into the middle, and then a split second later, the back edge of the ladder got to the front edge of the barn, and those were entirely different points in time. So they weren't synchronous. So it's not a paradox at all. It's just you can't have these Galilean ideas of synchronicity that we had before. And your book talks about it in terms of train cars being struck by lightning. If you had a train car, for instance, looking from above, right next to another train car, looking again from above, and at the same instant in time, lightning struck both ends, and then that lightning supposedly instantaneously fast would fire over to here and hit that guy. Well, this one's actually moving at some velocity v, and what it's going to do is, in this case, it's going to send the lightning down to the center, and that's going to flash a light. And in this case, it's going to do the same thing, send down to the center, and flash a light. In this frame, that light would flash, and you'd see the light would hit this end and this end at the exact instant. But in this frame, what's going to happen is the light is going to be sent out here from both sides, but this velocity of the train is going to cause this front part of it to go further away this way, away from the light. So it's going to take longer time for the light to reach the front mirror or the front detector than it takes to reach the back detector, which is actually moving towards it. So in this frame, you'll see that this one's first and this one's second, whereas these both are simultaneous in here. So yes, it turns out simultaneity is relative. In fact, two things aren't necessarily relative in every frame, and simultaneity is the cause of what appears to be a paradox in the ladder and the barn paradox. So we've actually finished the material for today. You're free to go. If you have questions, I know Victoria had one. If you have other questions, you can stick around. I'll wait for the last person to leave. If you need private time with me, I'm going to kill the recording and we can take it into a breakout room. And then anybody that waits while I'm in the breakout room, I'll come back and answer them when I come back. So thanks for coming, everybody. Hope you enjoyed it.
I have a quick question.
Yes, sir.
You mentioned that a student had found a formula sheet. I was wondering where we could find that.
I need to email that out. I have it. He emailed it to me. I just haven't sent it to you yet. Let me write a note about that so I don't forget.
Would you be able to post that on the Canvas page, or is
I'll do
email
that.
the best way to find it? Thank you. That was all.
No problem. Thank you very much. Anyone else? Aaron, Mario, Ryan?
I was gonna wait for a breakout room.
Okay. All right. Well, I guess I'll call it a day then. Or did I mishear you, Mario? What did you say?
Yeah, I was gonna wait for a breakout room.
I didn't hear that. Your volume went out.
Oh, I was saying I was gonna wait for a breakout room.
Oh, yes. Okay. I'll go ahead and give you a breakout room. Hold on a second. Ryan, I'll be right back. Okay, I'll be right there, Mario. It's not recording.